All right, so in section 4.2, we're going to be talking about how we measure the strength of association with correlation. So this is where we're going to have an actual number that tells us how strong the relationship between two variables is. So this is called the correlation coefficient, and it's a number that measures the, now this is incredibly important, not just any relationship, this measures the linear relationship. So the key here is the linear relationship. If we have a relationship between two variables that is nonlinear, then we can't use a correlation coefficient before we do some work first, which we're not going to cover in this class, but I just want you guys to know that it does exist. So some facts about the correlation coefficient is it's really hard to write correlation coefficient over and over and over. So what we do is that we represent this with the letter R. The values that we get are going to be values that bounce between -1 and +1. And if the values are closer to -1 or +1, this means that the association is very strong. If it's closer to 0, this means that the association is weak. So here we have some examples. So if we measure somebody's height in centimeters versus in inches, well, this is a 1-to-1 correspondence. You can easily go back and forth between these two measurements. So this would have a correlation coefficient of 1, the strongest you can have. So you can kind of think of that as these things are absolutely 100% related. Now if we look at the life expectancy between men and women in relationships, okay, that has a correlation coefficient of 0.98, so still very, very strong. We can also still see that there's a basic shape to this. Now, as we go down, we can see that there's a lot more spread as our R value gets smaller and smaller. So, one of the rules of thumb that I kind of like, it's not a hard and fast rule, is that if R is greater than 0.5, I like to say that that's a strong association. Otherwise, I say it's more on the weak side. So we can kind of use these pictures as a guide. Also notice that all of these are positive correlations. So they're all increasing, generally. This one doesn't have anything going on because it's 0. But they also have positive R values. So once we start looking at negative R values, that is when we're going to have negative trends. And these are also good, just little helpful things so that we can determine what our R value should be. So, the following scatter plot relates the size of diamonds to retail price. What we want to do is that we want to say something about the correlation between carat size and price, and we also want to estimate the value of R. So, if we look at this, what we can see is that there's a positive correlation. It's linear, so that means that we can use the R value. Now, if I look at the previous R values and I try to find an R value that has a similar grouping, like this one, well, I would say it's very similar to B, or 0.98 for my R value. It's a lot stronger than 0.72. So if I had to guess what the R value is, I would say R is probably between, I would say it's probably somewhere between 0.99 and the lowest I would go would probably be 0.85. So here's why this is important. In the future, we're going to be finding the R value using StatCrunch. You're always going to use technology to find it. It is an incredibly laborious process. I think in my entire career as a statistician, I've done it by hand once, and that was just to show that I could, and then I realized that it sucks. But it's important to be able to look at a scatter plot and kind of estimate what the R value should be, because sometimes what happens is that you're going to get an outlier that's going to skew your results. So for example, let's say that a very large diamond got stuck in there. but it had awful clarity and the color was gross. So even though it was a large diamond, let's say that its price was actually pretty low. Okay, so let's say it was about there. What the computer system is going to do, and actually what the math would do in general anyway, is that it would skew the data and be like, oh, well, maybe it's not as closely related as we thought, and we wouldn't get as good of a relationship, when really the relationship is more like this. So if you got that the R value was actually 0.7, but then you looked at the graph and you're like, well, it actually looks like it should be somewhere between 0.85 and up, well, that gives you an indicator that maybe you need to be looking out for an outlier. All right, so the very last thing I wanted to look at is that we have this scatter plot that has the miles per gallon versus the weight of a vehicle. Okay, so what we want to do is say something about the correlation between the miles per gallon and the weight. So if we look at this, we would say that it has a nonlinear, and it has a basic shape, so I would say somewhat strong. Negative relationship. Now, notice that even though we just talked about the R value, I didn't say what I expect the R value to be. Why is that? Well, the reason I didn't say anything about what the R value is because this data is non-linear, so we can't talk about the R value just yet. All right, in the next video, we're going to be talking about how to fit a line to linear data.